energy first thing, and then we have a formula for semi-empirical mass formula. And nuclear spin, I doubt if we can do it, but let's just finish off with this pairing energy. So yesterday we have seen that if we consider the semi-empirical mass formula, there are basically five parts to it. Okay, the first three part basically, which is called the Coulomb energy, the surface term, the volume term, are basically derived from what we know as the liquid drop model. And the next two, which is the asymmetry part and the pairing part, are not derived from the liquid drop model. The asymmetry, we have seen that it can be actually explained based on cell structure or some other models. Okay, and Pauli's exclusion principle plays a very important role there. And today what we're going to see is pairing, which can also be explained based on Pauli's exclusion, the shell model. So then it says that a single model, which was the liquid drop model, was not efficient enough to actually explain all of it. Okay, it had some drawbacks, so we had to take help from others aspects. And then it also meant that quantum mechanics also plays a very important role in nuclear physics. So when we talk about pairing energy, it simply means that there are protons and neutron pair which tends to form or bond together. Basically, there will be two proton and there will be two neutron, and they will actually form a pair. Now, if it happens that one of the proton, one of the neutron, or one of the proton is left alone, okay, it doesn't have any other neutron or any other proton to pair to, it actually reduces the binding energy. So this is a very important thing that to understand, that basically pairing energy can increase or reduce the binding energy depending on whether you have an odd structure, an even odd structure, or an even structure. Okay. So by odd, I mean we have got odd protons, odd neutron. Odd even mean odd proton, even neutron, or odd neutron, even proton. Even means even proton, even neutron. Okay. So we have to look into these factors to know what is the value of the pairing energy, for which I think I explained a lot yesterday. Then we have got an even number of particles. Okay, we have got an even number of particles, which is actually more stable than an odd number. Okay, due to spin coupling effect. So if you have got an even number of particles, that means you have got even number of neutron, even number of proton. It is going to basically form a pair. That means it is going to be more stable. If it is more stable, that means I need more energy to break it. That means it is having greater binding energy. So that means that will be added. So it will definitely be a plus value. But if it is even odd, okay, all odd, there is going to be something which is not pairing up, and this will actually result in making the nuclear spin. So this is from the liquid drop model. This is from the nuclear shell model, which we are going to look into in third unit. Okay, we have a very elaborate idea of nuclear shell model in your third unit of the syllabus. So if you just look into the binding energy, don't get confused. You can write it down as e to the base b or just b. I'm just written it b here. Don't worry. So if you look into the binding energy, we know the terms here. We basically know that this is nothing but your volume term. This is the surface term which reduces the binding energy. This is the asymmetry term which is again reduces the binding energy from Pauli's exclusion principle idea. This is the Coulomb energy which is also reducing the binding energy, but the effect is not that much, because yesterday we saw that the constant of this particular value is just 0.6 something. Okay, 0 point something, some value. Okay, 0.6 or something. So that means it's going to be a very less impact. On the other hand, if you look into this pairing energy, we see that there is a substantial impact. Depending on what kind of model we are using, we can actually have different values of this delta, which is the pairing energy constant. So for me, the model that I've considered has a to the power half. If you consider any other model, this a might be some other value, which will have basically nothing but a will be same, but the parameters will be different here. There is one which is 3 by 2. Okay, if you consider this formula, your value of pairing energy would be 33.5, or you can take 34 also. So it will be plus 34 for even, minus 34 for odd, and odd even it will be more or less 0. So we've seen that. So please don't get misguided. Whatever I have written is from a different model. If you read a book, you get a different model. Don't be confused. You can write that also, no problem. This is correct. That is also correct. So based on this model, which I have considered, we have the value of the pairing energy as plus 12 for odd. Okay, minus 12 for even. So again, don't get confused. If it is a minus here, if you put the value of minus here, this becomes plus. This becomes plus, that means this will add to the binding energy. That means if it is even, it is more having more binding energy. So it is more stable. So just the notation, okay? So don't get confused. Plus 12, if you put here, that means the entire value will be subtracted. So that means the binding energy will reduce. So odd will reduce the binding energy. On the other hand, if you have got odd even, the value is 0. Okay. So these are empirically observed. You might not have a very strict experiment for these, but there are observed experimentally based on theory, based on logic. All these were used to actually do this. Okay. Now, what is this binding energy and the semi-empirical mass formula, and where we can actually club them together? It's simple. We basically have the binding energy curve. I think I have shown it to you yesterday. We basically have on the y-axis, we have got binding energy per nucleon. And on the x-axis, we have got nothing but called the mass number. And if we basically plot a graph, we actually get a binding energy curve. So these dotted lines are more or less observed, okay? So these are observed. So basically nothing but you can say experimental, okay? So these are observed, these dotted lines. But this solid line that we can see, this solid line, this is nothing but coming from the semi-empirical formula. This is coming from semi-empirical formula. So do they agree? Yes, in a lot of points they agree. In the lower range, usually they don't agree much, okay, although it is being fitted, depends on what kind of model you are using, but mostly it agrees above z is equal to 20. Now you might say that how does it agree, because I can see that there are some peaks here, there is some peaks here. So there are certain elements which are actually showing extra stability. If you have read about the term magic numbers, which we are going to look into the third unit, there we see that something like lithium, something like helium will basically have more binding energy per nucleon. That means they are more stable compared to the neighboring nuclei. Okay. So based on this, we are actually having an extra stability, which actually cannot be always explained based on semi-empirical mass formula. So semi-empirical mass formula gives the general trend, which agrees with most part of the curve. Okay. So this is experimental, this is the observed part. So that means we can actually compare the binding energy from experimental and semi-empirical mass formula. So that is important. But then, as I said, it is always valid for a greater value of mass number. Okay, because then if you have more mass number, Coulomb energy, asymmetry, pairing, all these things becomes more and more important, because the asymmetry will become more, the pairing there will be a problem, because if you consider higher order atoms, let's say for example a very heavy atom, let's say uranium 235, it has got more neutrons compared to proton 92 and 146 and so on, right? So if I've got more number of neutrons, that there is some kind of asymmetry which is coming in. So if you look into the periodic table and if you go for a mass number greater than 30, you are going to come across elements which has got more neutrons compared to proton. So that means there is going to be more instability there. And that is the reason that we basically have something which is called the value or the agreement of the semi-empirical mass formula at a greater mass number. So in some books, they do also do write above 20. Don't get confused. There is no such strict rule. Okay, sometimes 20, sometimes 30 is fine. It just depends on what kind of model you are using. As I said, for semi-empirical mass formula, there were at least 4 to 5 models, out of which some of the models are very well. Okay, so some of the models we can always use. Okay, we'll come back to the numerical. I hope all of you are ready with a pen and a paper. And this time I want answer, okay, from someone who has not answered. Many of you keep answering, but try, okay. It might take some time, okay, but this will make the concept of semi-empirical mass formula and binding energy from the experiment clear. So if you want to know the values here, so let's say I will actually take out a point. Suppose at this particular point, okay, I want to ask you that what will be the binding energy per nucleon as per semi-empirical mass formula, and what will be the binding energy per nucleon as per the experimental observation. So how are they plotted? Okay, for this particular problem, I have given you this example because I think this is important. So the question is, use semi-empirical mass formula. You have to evaluate the binding energy of calcium 40-20, right? So basically 20 is the number of protons you have, and then 40 minus 20, that means again 20 is the number of neutrons that you have. You have to use the semi-empirical mass formula to calculate this. Also, you have to find out the actual binding energy. The question is, how do you find out the actual binding energy? But before we go to actual binding energy, how do I find out the semi-empirical mass formula binding energy? From this particular formula. You see this. You know what is the value of A, B, C, D, and delta. I've already given it. It's 20, 20, so it's even. So you can just put the value as nothing but 12, minus 12. So you can just put the value, this is minus 12, and then do the calculation. A is given to be 40 everywhere, N is 20, Z is 20, okay? So you basically see that these things will be there, okay? And then you can do your calculations normally. And then what you see is that you will be getting one value of binding energy from this particular calculation. So please remember, yesterday I don't have it in my slides today, okay? The value of A, B, C, D, and delta. If you don't have it, you can just Google it. If you have not written it, I have no problem with using the internet. So you can Google and find out what is the value. Put the values here, plug in the values here, find out what is the binding energy. Okay. Next, you have to find out the actual binding energy. So how do I find out the actual binding energy? It's very simple. Same thing we are going to do. We are going to just find out the mass difference. So basically, you're going to take mass of proton multiplied by 20 plus mass of neutron multiplied by 20. Find out what is the answer. And then you find out what is the mass of calcium. Okay. So in U, okay, U unit, atomic mass unit, AMU units, okay. So you also can Google here, okay, because I think I should have given it here, but anyway, you can just check it. This is all standard values. It is 39 point something, I guess. Do the calculation, take the difference, and you can find out what is the mass defect in AMU. Multiply it with 931.5, you get it in EV.